Space travel is exciting thanks to the many discoveries waiting to be made. However, some places in space, such as distant stars, are deemed unreachable due to the limits of human technology. But that is not going to be the case for long thanks to a new invention by a NASA genius that allows us to visit faraway stars like Proxima b. What is the light speed engine and how fast is it? Keep watching this video as we bring you how a NASA genius invented a light-speed engine to visit Proxima b. Have you ever reached out to touch the stars in the night sky? Those tiny, shiny objects peppering the sky are actually large, but they appear tiny because they are trillions of miles away. Humans have made massive advancements in space travel, allowing us to reach places that our forefathers wouldn't have dared dream of. However, the stars in the night sky are so far away that our current modern rocketry cannot handle a visit to them. And while you might not see them, these stars are sometimes orbited by planets, in which case they are known as exoplanets. An exoplanet is an abbreviation for extrasolar planet. It is a planet that orbits a star other than our Sun. In a nutshell, they exist outside of our solar system. Now, the universe is thought to contain approximately 200 sextillion stars, that is 2 followed by 23 zeros. If there is at least one planet for every star, then there could be sextillions of exoplanets out there. And one of these planets is Proxima b, which is the closest exoplanet to us. This planet orbits its star in just 11.2 Earth days. Its minimum mass is estimated to be 1.2 Earth masses. It is 0.0485 astronomical units or AUs away from its star, which means it is approximately 20 times closer to its star than the Earth is to the Sun. Because it is part of a triple star system, the host star Proxima Centauri is also known as Alpha Centauri c. It is a variable star that causes flares and abrupt brightness changes. This means that any atmosphere Proxima Centauri b may have will most likely be destroyed by the star's UV and X-ray emissions. Aside from its distance, Proxima Centauri b is interesting because it's located in the habitable zone of its planetary system. It is similar to Earth in many ways, making it a popular topic among astronomers. However, there is still much unknown about Proxima Centauri b. First and foremost, we don't know whether or not this exoplanet has an atmosphere. The exoplanet's age is also unknown, and we don't know if it has moons. Proxima Centauri b is located 4.2 light-years away from our solar system. It is part of the Alpha Centauri triple star system, which also includes the dwarf star Proxima Centauri. Proxima Centauri b is significant to researchers because it's the nearest exoplanet to us, but it's also a fascinating subject because it's roughly the size of our planet. And Proxima b's composition and location in the habitable zone make it even more Earth-like. And this brings us directly to another reason scientists are fascinated with Proxima b and would like nothing more than to visit it. Is there a possibility of life existing on Proxima b? Scientists have spent decades trying to establish whether life can exist in the universe outside the solar system, and Proxima b is a good candidate for exploration. The presence of liquid water on the planet's surface is critical to habitability. While visible and infrared light simply warm a planet, high-energy radiation, X-rays, and extreme ultraviolet and particles pose a threat to gases and liquids because they can be eroded away and escape into space. And because Proxima b receives significantly more of this radiation than Earth, it is critical to determine whether the planet has been able to maintain its water and gases in general over the course of its 5 billion-year history. Researchers have discovered that Proxima b currently receives 60 times more high-energy radiation than Earth, and that the total since formation is approximately 7 to 16 times higher because the Earth was also irradiated more strongly in the past. Although the amount of water on the planet at the time of formation is unknown, calculations show that Proxima b may have lost about 1 ocean's worth of water due to early irradiation in the first 100 to 200 million years after formation. What happened after that point is unknown. The planet could have continued to lose significant amounts of atmospheric gases, eventually becoming a dry, atmosphereless world. Or perhaps it could have kept most of its atmosphere and liquid water on the surface, making it hospitable to life as we know it. Both options are still open. Although more research is needed, studies have concluded that the presence of liquid water on the surface today cannot be ruled out, and thus Proxima b can be considered a viable candidate habitable planet. And to investigate the possibility of Proxima b having surface water and an atmosphere, researchers used a sophisticated 3D model and explored a wide range of atmospheric compositions and water inventories. They discovered that liquid water may exist on the planet's surface only in the sunniest regions, either in the planet's hemisphere facing the star or in a tropical belt. However, what better way is there to explore Proxima b than sending a probe to the exoplanet? And yet this is where the problem lies. Proxima Centauri is 4.2 light-years away from Earth, or about 25 trillion miles or 40 trillion kilometers, which would take approximately 6,300 years to travel using current technology. A journey of this magnitude would take many generations. Indeed, the vast majority of those involved would never see Earth or its exoplanet counterpart, and these humans would need to reproduce with each other throughout the journey in order to arrive at Proxima Centauri with a healthy crew. Apollo 11 traveled at around 40,000 kilometers per hour, which would take over 100,000 years to reach Proxima Centauri. However, spacecraft have become faster in recent years. The Parker Solar Probe travels at a speed of more than 700,000 kilometers per hour, or about 0.067% the speed of light. NASA's New Horizons probe completed its 3 billion mile or 4.8 billion kilometer journey to Pluto in 2015 after 9.5 years. The spacecraft reached speeds of up to 52,000 miles per hour or 84,000 kilometers per hour, and at that rate, New Horizons would take 54,400 years to reach Proxima Centauri. And NASA's Juno probe reached speeds of around 165,000 miles per hour, 265,000 kilometers per hour, as it entered orbit around Jupiter. At that rate, a probe would arrive at Proxima Centauri in approximately 17,157 years. So what technologies are available today to launch visitors in the direction of Proxima b? Ionic propulsion has been developed to propel unmanned space probes faster across the universe. The most recent craft use solar power to move their ion thrusters, resulting in a very fuel-efficient system that requires only a small amount of xenon or another propellant for the journey. Because of its fuel efficiency, ionic propulsion would be the most practical and cost-effective method of traveling to the nearest star. Deep Space One, or DS-1, was the first spacecraft to use ion drive technology in 1998, and during its mission to test the new technology, DS-1 achieved a velocity of 35,000 miles per hour, or 56,000 kilometers per hour. At that rate, it would take 81,000 years to reach Proxima Centauri. At the moment, the quickest way to travel through the universe is with gravity assist, a method in which a spacecraft uses the gravity in orbit of nearby planets to propel itself at high speed. It was used to catapult the Mariner 10 spacecraft to Mercury in 1974, where the gravitational field of Venus was used to propel the vessel forward. The NASA Helios 2 space probe became the fastest man-made object ever made in 1976, reaching a maximum velocity of more than 150,000 miles per hour, or 240,000 kilometers per hour, using the orbital speed obtained from the Sun's gravitational pull. Now, at this rate, it would take between 19,000 and 76,000 years to reach Proxima Centauri, depending on the velocity of the spacecraft. However, there is also nuclear thermal and nuclear electric propulsion. This type of propulsion has never been used in a spacecraft, but it produces thrust by using nuclear engines. Nuclear thermal propulsion, or NTP, and nuclear electric propulsion, or NEP rockets both use uranium or deuterium-based reactions to propel the spacecraft via nuclear fission or nuclear fusion rather than chemical propellants. NTP, NEP would be cost-effective and allow for lightning-fast transport through space if it could be safely perfected. The time required to reach Proxima Centauri could be reduced to 1,000 years using this method. But 1,000 years is still a long time for humans. There is, however, another effort going on to send missions to the star known as Project Breakthrough Starshot, using an interesting method of propulsion. The aim is to develop a spacecraft that can reach the stars within a human lifetime. The spacecraft works by avoiding a big issue that modern rockets have: mass. Mass is the bane of accelerating objects to great speeds. It takes a tremendous amount of energy to significantly increase the velocity of a heavy object. As a result, if the goal is to reach a distant star in a reasonable amount of time, say within a generation, the spacecraft must be extremely small and, as a result, robotic. Furthermore, it still requires an extremely energetic boost to get it up to speed. This is the basic idea of Breakthrough Starshot. Create a Starship-equipped nanocraft, give it a powerful push, and watch it zip off to Proxima Centauri at more than 130 million miles per hour or 216 million kilometers per hour. And to increase the chances of some of the spacecraft reaching the star, the brains behind the project plan to send hundreds, if not thousands of them. Isn't it simple? Well, yes, in theory, but in reality, it will require a tremendous amount of effort, numerous technological breakthroughs, and of course, a large sum of money. But what better time than now to embark on such a life-changing mission? So to travel quickly to another star, a spacecraft must be small. However, it also requires a strong push to get started. One possibility is to borrow a tool used by pirates to plunder the seven seas, the humble sails. Starship's sails, however, would catch powerful beams of laser light rather than wind. The idea of sailing in space is surprisingly not new. In fact, the first mention of cruising through space on celestial winds was in a 1610 letter from astronomer Johannes Kepler to his friend Galileo Galilei. With ships or sails built for heavenly winds, some will venture into that great vastness, Kepler wrote. However, it wasn't until the work of Soviet rocket pioneers Friedrich Sander and Konstantin Tsiolkovsky in 1924 that the true potential of using sunlight to sail through space was fully recognized. The idea was then taken a step further in the 1960s by Hungarian astrophysicist George Marks, who wondered if a directed beam of energy rather than sunlight could be used to propel such a spacecraft. In the 1970s, American physicist and science fiction writer Robert Forward took the lead, further developing the light sail concept. Forward's research led to the publication of a paper in the Journal of Spacecraft and Rockets in 1984 titled Round Trip Interstellar Travel Using Laser-Pushed Light Sails. In it, he explained how the laws of physics did not preclude the use of light sails to travel to other stars. Forward did note, however, that whether it can be engineered and is financially or politically feasible is left to future generations to determine. Well, future generations are here and ready to prove it can be engineered. Despite the daunting, multifaceted challenge of interstellar travel, Forward developed actual plans for an ultralight interstellar probe powered by microwave lasers or masers in 1985. In the 1990s, NASA Glenn Research Center scientist Jeffrey Landis jumped into the fray to expand on Forward's basic design. But Star Wisp never took to the skies. Then Cosmos 1, the Planetary Society's own solar sail, was launched in 2005 but failed to reach orbit. Finally, though, nearly a century after the concept of sailing on sunlight was first detailed, the Japan Aerospace Exploration Agency, JAXA, successfully launched the interplanetary kite craft accelerated by radiation of the sun, Icaros, which hitched a ride to Venus with the climate orbiter Akatsuki. Once in position, Icaros spun at a rate of 25 revolutions per minute to unfurl its 46-foot wide or 14-meter sail, which was only 0.0003 inches or 7.5 micrometers thick. That is roughly one-third the width of a human hair. Within a month, JAXA reported that photons from the sun were indeed accelerating Icarus, albeit by a relatively modest 890 miles per hour, or 1,430 kilometers per hour. And by utilizing adjustable LCD panels embedded in the sail's edges, the spacecraft was able to adjust the force pushing against it, allowing it to change orientation at will. After the technology behind light sails was proven to work in space, Israeli-Russian billionaire Yuri Milner stepped up a few years later. Milner casually asked scientists to look into the idea of interstellar spacecraft that could sail on light. The task took the team 6 months to thoroughly research. By early 2016, the researchers were convinced that an interstellar mission was feasible or would be soon if technology continued to advance at its current rate. So Milner officially launched the Breakthrough Starshot project with a $100 million personal contribution to fund proof-of-concept research and development not only of light sails, but also for other advanced technology required to send a craft to another star within a generation. Since then, devoted scientists and engineers have worked tirelessly to make this lofty goal a reality, taking advantage of additional funding from multiple NASA grants. The initiative has made some significant progress and is still addressing some issues. For example, if Breakthrough Starshot is truly capable of accelerating a spacecraft to 20% the speed of light, that craft will need to be roughly 1/1000 the mass of Icarus, which weighs approximately 4.4 pounds or 2.2 kilograms. That means Starshot will have to fit everything it needs for a 4-year interstellar journey into a suitcase no bigger than a couple of paper clips. There is, however, something working in favor of Starship, and that is the famous Moore's Law. It predicts a biennial doubling in the number of transistors that can fit on a microchip, allowing for smaller, more powerful devices. There are already tiny electronics that can do some pretty amazing things. Engineers, for example, have created low-cost cameras weighing less than a gram and capable of capturing resolutions of at least 200 by 200 pixels. Of course, by today's smartphone standards, that's not much, but it's sharp enough that one mounted to a Starship could resolve exoplanetary continents and oceans as it zips by. And the Breakthrough Starshot team has set an even higher standard. They are hoping that technological advancements in the coming years will enable ultralight cameras capable of taking 20 megapixel photos. And the sail itself must be extremely light. Fortunately, the cost of producing high-quality nanoscale materials is steadily decreasing, but when it comes to light sails, weight isn't the only issue. To avoid being vaporized by 100 gigatons of laser light, a sail must only absorb, rather than reflect, about 1 out of every 100,000 photons that strike it, according to the scientists. That presents a significant material challenge. The team is actively looking into creating such a sail out of graphene. But there are reasons to be optimistic about the chances of Starship. The Starshot team has successfully launched other prototype crafts, testing various aspects of their design and technology. For example, researchers launched 6 tiny craft into low Earth orbit, each weighing about 0.14 ounces or 4 grams. Named Sprites, these were chips that contained solar panels, computers, sensors, and communication equipment on a square frame that was only 1.4 inches, 3.5 centimeters wide. And while the researchers were unable to communicate with the majority of the sprites, they did receive a signal from at least one of them, demonstrating that such miniaturized communication and power systems can function in space. The initiative then sent another tiny prototype 100,000 feet or 30,500 meters above Earth to photograph our planet's surface. During its flight, the test captured approximately 4,000 images, sparking much speculation about what equivalent images of the 2 known exoplanets near Proxima Centauri might look like. There is, however, another interesting type of propulsion that NASA is actively looking at to enable us to send missions to Proxima b, a light-speed engine with an astonishing amount of speed. This project is headed by NASA engineer David Burns, and it all started from his personal projects during his spare time. He's developed an engine concept that he claims can accelerate to 99% the speed of light. And the best part of it is that this machine works without using a single drop of propellant. He posted it to NASA's technical report server under the title Helical Engine, and it works by taking advantage of how mass can change at relativistic speeds, those close to the speed of light in a vacuum. Of course, Burns' paper has generated buzz comparable to the early days of the EM drive. Yes, there have been reports that the engine could violate the laws of physics. Burns describes a box containing a weight that is threaded on a line and has a spring at each end that bounces the weight back and forth. In a vacuum such as space, this would wiggle the entire box, with the weight appearing to stand still, much like a GIF stabilized around the weight. Overall, the box would remain in the same position. However, if the weight's mass increased in only one direction, it would generate a greater push in that direction and thus thrust. Now, this should not be entirely possible according to the principle of momentum conservation, which states that the momentum of a system remains constant in the absence of any external forces. Thankfully, there's a but, a special relativity loophole. Objects gain mass as they approach the speed of light according to special relativity. So if the weight is replaced with ions and the box with a loop, the ions can theoretically move faster at one end of the loop and slower at the other. Burn's drive, however, is not a single closed loop, it's a helical, like a stretched spring, hence the name helical engine. This engine accelerates ions in a loop to relativistic speeds, then varies their velocity to change their mass slightly. To generate thrust, the engine then moves ions back and forth along the direction of travel. And something else that makes this machine very interesting is that it has no moving parts, except ions traveling inside a vacuum line that are trapped inside electric and magnetic fields. That means the engine has fewer chances of breaking down in space. The helical chamber is 200 meters or 656 feet long and 12 meters or 40 feet in diameter. It would require 165 megawatts of energy to produce 1 newton of thrust. While that requirement might seem high, it is worth it because the engine can attain 99% of the speed of light. And there are other forms of spacecraft propulsion that scientists are investigating to allow us to reach Proxima b. There is nuclear pulse propulsion, for example. Nuclear pulse propulsion was first proposed in 1946 and was briefly studied by a team at Princeton University in the 1950s and 1960s. It contains a spacecraft equipped with a propulsion system exploding a series of thermonuclear warheads behind it, creating a wave of energy that's absorbed by a pusher pad, which then drives the vehicle forward. But there are several problems. The cost of such a spacecraft would most likely be around $2.5 trillion, and nuclear testing bans make it nearly impossible to study the method of propulsion to see if it could ever be made feasible. Nonetheless, estimates suggest that a spacecraft using this method could reach 5% of the speed of light, or 33,353,083 miles per hour, which is not so bad. And we also have fusion rockets. Fusion rockets were briefly investigated in the 1970s and are another potentially fast way to traverse the galaxy. Deuterium and helium-3 pellets are detonated inside a fusion reactor to generate plasma energy to power the rocket in this type of spacecraft. Again, there are a number of challenges that must be overcome in order to make this concept a reality. The most significant of which is that helium-3 must be mined in space because it's not readily available on Earth. However, a craft could travel to Proxima Centauri in just 36 years if it gradually accelerated up to 12% of the speed of light, or 80,473,995 miles per hour. We also have the antimatter engine. Star Trek fans will recall that warp-capable Federation starships are propelled by a matter-antimatter reaction that generates massive amounts of energy. Antiparticles have the same mass as their corresponding particle but the opposite electrical charge. It wasn't until 1928 that Paul Dirac revised Einstein's E=mc² equation to allow for a positive or negative value for energy. An antimatter engine slams hydrogen and antihydrogen particles together with the resulting reaction producing enormous amounts of energy, as well as subatomic particles traveling 1/3 the speed of light, which are then traveled out of a magnetic nozzle to produce thrust. It is thought that a spacecraft powered by an antimatter engine could travel at half the speed of light and arrive at Proxima Centauri in 9 years. But on the negative side, antiparticles are extremely rare and difficult to store, and scientists have only been able to create 20 nanograms of antimatter through collisions inside large particle accelerators, with the cost of producing even 1 gram of antimatter reportedly costing trillions of dollars. But hypothetically, what if NASA goes full metal and tries to send humans to Proxima b with their descendants expected to land on the exoplanet? Choosing a crew for such a multi-generational space journey would be a difficult task. Important parameters include the number of men and women on the crew at the start, their age and life expectancy, infertility rates, the ship's maximum capacity, and so on. It also necessitates rules governing the age at which procreation is permitted, the degree to which parents can be related, the number of children they can have, and so on. It's a messy plan with a lot of unknowns, by the way. According to scientists, the chances of success do not reach 100% until the initial crew has 98 settlers or 49 breeding pairs, meaning a minimum crew of 98 settlers is required for a 6,300-year multi-generational space journey to Proxima Centauri b. Interesting to note, though, that the chances of disaster due to accidents or plagues may be much lower than the chances of disaster due to social factors, such as conflict, that can doom the mission. Do you think humans ever stand a chance to reach Proxima b? Let's hear your thoughts in the comments section below.